Next question that we'd like to put is what is being implemented or still has yet to be implemented, but it's coming in commodity supercomputing networking in order to be able to limit the impact of a failure. I think I'm supposed to take this question. So I'll take it. If you look on fault-tolerant, and it was said a couple of times here, you need to look on the entire system, which includes the software and the hardware and all the components. Right? It's a one solution. Now, in every part of it, there is something that you would like to have. So you can have multiple rails if a network card failed on a server. You can have multiple switches. You can have, I think you can pretty much predict 70% of failures before they happen. And if you have tools that gives information about that, and you have some spare nodes, then you can do some checkpointing from the software and take out the node that's going to fail and put the spare node that you had there. So there's multiple items, and some of those items are really coming. And I've talked with multiple NPI providers, for example. Some of them are open source, and they're working on such projects. If you look on the networking itself, an interesting capability in the networking that might help here is if the network will become something that is more self-healing network. Which means that if something happened in the network, if cables got corrupted or you had an airplane landed on your cable, if the network is smart enough to figure that event and bypass the damaged cable, for example, and moving all the traffics into alternate routes, or if a switch failed and you go around that switch, and you still keep the application running, you do want to provide an indication to the user or to the admin that something happened and you should take a look or she needs to take a look. But if the network will be able to capture those items and be able to react in real time to those failures, that's another part that helps fault-tolerant. So those kind of things are coming, and there is work being done on them, both in the NPI side to be able to use spare nodes instead of failing nodes, and using checkpointing, and both in the networking side to be able to detect in real-time failures and bypass those. That was my question.
Let me add a couple of things. I think there's one area here that is a little bit non-obvious, and it's if you look out in the cloud environments, virtual machines are one of the ways that people use to improve their overall fault tolerance. And certainly at a compute node, virtual machines work very well. Not necessarily in high performance computing now, but in the network, as pieces are implemented to make the virtual machines more network friendly, that will allow us to put layers in place to overall add improved fault tolerance. A lot of HPC people don't use virtual machines right now, but if the penalty for running a virtual machine is reduced enough, I think it will become more and more common for that to occur.
Well, I find pain points just in the processes themselves and failures in the processors. When you look at, you get very, as you start to get spikes in the computation load, which then heats up the chips and gives you problems that way. When you get power spikes, when you first start out the computation, you get power spikes along those lines. And so that to me is one of the bigger pain points that I've seen in work that we've done. And I was wondering about what you think about, what we do is a lot of software, building in things in the software to make sure data integrity and things like that, to make sure that we're checkpointing, we do checkpointing and that make sure that we are on the path to getting the right answers. And so I'm just kind of curious about what, I don't know if that was listed as one of your pain points, but the processing elements themselves, chips.
Yes, I think you're basically getting down to the real hard problem to solve. Recovering from when your actual compute node fails, because you do all these things and you move you kind of moved all the common parts the fans, the disk drives, and you've got recovery built and redundancy built on all those parts. And yet, so now you're down to the most common part that fails is the actual compute node. And that's probably the area that we'll be doing most of our future work on.
And I think this actually touches on a completely different topic, right? Which is, how do you prevent failures? And I think in the instance that you're talking about, you end up with a couple of different things, right? So you get power spikes, and sometimes that's because of, as the CPU starts to load increase, right? So that goes back to the chip manufacturers, that they need to do something around that. Or is it a power spike, and are you properly power conditioned? Is it in the PDU or the UPS system that you're connected to? And cooling certainly is a big problem, right? Because they've shown, if you look at some of the studies, that a 10-degree increase in temperature increases the failure rate of an electronics component by like 3 or 5x. Right? So you have to be very careful about the ability to cool these things. And that also goes back to the ability to cool it not only within the rack, but creating hot spots within the rack. Because if you're doing air cooling, you create different pressure zones right at the bottom and at the top, and they tend to overheat faster. And liquid cooling certainly is becoming a lot more predominant, I think, in a lot of the systems that we're installing. Water-cooled doors is becoming very prevalent, right? Rather than trying to do it through cracked units and air-cooled, or through hot aisle containment systems, right? So now you're trying to prevent the fault, and that, I think, probably ends up being a really long other topic.
So exactly, and I'd just add some comments. So prevention and also the forecasting of the error is very important, especially for the maybe the next generation of the millions of components of systems. So not just for the dynamic fault tolerance or control, but also the prevention of the failure and the forecasting of the failure is very important. For example, we are running 10,000 cores of big clusters of Appro, and we always keep checking the memory, single error memory correction. And if it's overcome to some threshold, we will change it before the real serious double error corrections happen, error happens on the memory. So, but unfortunately, so far, I think there is no such a feature on the network device itself for the forecasting or some detecting of the failure happens in near future. So the memory system is working well in such a viewpoint, but the network system also must have such a feature of the detection of the near future error happens.
I just have a question about disk reliability. The network-wise disk like the GPFS or Lustre usually is very expensive and have a limited bandwidth when you spend like thousands of nodes. So we were trying to sometimes use a local disk. Local disk, although it's slow, but it's naturally scalable. But we found out the local disk is cheap and very easy to fail. Fail rate is pretty high. Sometimes after a couple of days, it failed. And so I'm certainly wondering if there are some opinion. I mean, I heard that many computer centers just abandon using local disk. But we were just wondering if there any opinion in this area.
I think that's probably one of the major areas that we're looking at right now. Because, as you mentioned, whenever you get down to paying for your disk storage, you use so many disks that you inherently get a fairly high failure rate. And I've been on projects before where essentially the disk replace person had to have skates on their feet to keep up with the number of disk failures. And so I think that's a very common thing on the disk systems that exist today. And it's even exacerbated more whenever you look at the number of disks that you have to meet your bandwidth requirements. Today, you almost always have to have a huge number of disks to meet a reasonable 100 or 200 gigabyte a second bandwidth out of that. And so I think you're going to be seeing, particularly from us, and I suspect other people will also be providing over time, solutions to that particular problem that will allow you to reduce the number of disks that are used and hence increase your failure rate. But at the same time, one of the things you want to do there is also keep in mind that you want to actually increase that bandwidth so that you can reduce your checkpoint time. So that's probably one of the major areas that we're looking at, and we see that as probably the biggest data gap that exists in today's supercomputers.
Just wondering if you're aware of any work being done when you get down into some of the harder problems you mentioned earlier. I've experienced situations where on a longer running job of multiple nodes, obviously, one node, if it does have a CPU or a particular core failure or a problem with an interface card, it's running slow. Now, the synchronization of the jobs are going to run as slow as the slowest link. So, are you aware of any dynamic checkpointing, offloading type of algorithm that would say, okay, I know I'm supposed to perform at this level. We're seeing a bottleneck on a particular node, taking that workload, dynamically moving it to a provisioned resource, provisioning and allocating it. Probably gets into some pretty complicated type of things. But I just wondered if you do any work along those lines, allowing your job to continue running and then speed back up after correction.
I think for a large number of jobs, that's where you're going to see the people start using virtual machines and virtual clusters. I don't think that the environments are mature enough right now. If you look at the current checkpoint restart environments. But as you mentioned, you really don't want, you want to be able to tell an operating system layer your expectations for that, rather than having the application developer embed that into their code, because the applications are complex enough as it is. And so I see a lot of potential for the virtual machines, and I think that it's going to be problematic until people start running virtual machines in HPC environments. That's my own view on that.
You've just in the view of virtualization and provisioning. Virtualization helps you to provision when you need to provision less than a single machine. If you look, there is some development on some probably tools that are exist today that gives you the ability to provision a system and change the provisioning and do it up to one node component. If you want to provision more than that, and you want to provision to a core or less than a core, then where virtualization comes inside. But it's not a must if you want to do provisioning or dynamic provisioning.